For day 15, I wanted to concentrate on the very beginning of the chapter where we looked at the relationship between impulse and momentum. And then I wanted to, after just going over that really quickly, do 2 examples. So, in chapter 5, we learn Newton's second law, F equals ma, where acceleration, of course, is a derivative of velocity with respect to time. In chapter 8, we're introduced to a new term, and it's called momentum. Momentum is simply the mass times the velocity of an object, and therefore it has direction. Well, if our mass is constant, we can write Newton's second law in a new way, because the derivative of momentum with respect to time would be found using the product rule. But of course, if mass is constant, this first term goes away, and so we see that for a constant mass, the derivative of momentum with respect to time is equal to the mass times the acceleration. This gives us a new way to write Newton's second law as the derivative of momentum with respect to time is equal to the force. So, if we take that equation and we rearrange it, we just multiplied through by a dt. The dt and the dp tell us that we probably want to integrate. And so what we find here is this is the product of a force. It's an integral of the force over the time. So a force is acting for a certain amount of time. We call this quantity impulse. The integral of dp is simply going to be the change in the momentum, because you just get P initial over P final is our endpoint. And so we call this relationship the impulse-momentum relationship. This is the impulse. This is the change in momentum. And it's just a different way of us looking at Newton's second law. And we're going to be able to use this for some different types of problems. Just a little aside notice here that if we had a graph of force versus time, some curve, the area underneath it, the area under the curve, is equal to the impulse. So now I'm going to do some example problems because of the fact that, for one, we have to review our vector knowledge, and then we're also going to see how we can use these relationships. So in our first problem, we have 2 vehicles approaching an intersection. So the first one, I'm going to call it mass 1, is coming from the east to the west, so it's going to the left with a speed of 15 meters per second, and mass 1 is 2,500 kilograms. Mass 2 is a little smaller, it's only 1,200 kilograms, but it's traveling upwards with a speed of 22 meters per second. So both of these vehicles have momentum. They have momentum in different directions because momentum is a vector. And we're asked to find a couple different things. We're asked first to find the momentum of the system in the x and y direction. Now, because these 2 objects are moving perpendicular to each other, the x and y momentum of the system is only actually dependent on one of the objects moving. So for instance, the x momentum is due to mass 1, the y momentum is due to mass 2. So for mass 1, which is the truck, its momentum in the x direction is its mass, 2,500 kilograms, times its velocity, which is minus 15, because it's a vector, we have to use that. And so this gives us a net x momentum of minus 37,500. We don't have any sort of clever units for momentum. We just call them kilograms meters per second. The y momentum of the system is due to mass 2 because it's moving in the y direction. So we have 1,200 kilograms times the 22 meters per second. It is positive velocity, and that gives us a y momentum of 26,400 kilograms meters per second. To figure out the total magnitude of the momentum, that is found using the Pythagorean theorem. I take the x component squared plus the y component squared, take the square root of that, and that's going to give us 45,861 kilograms meters per second. And then finally, to figure out the direction of the net momentum is the angle whose tangent is equal to the y component over the x component. Just to remind us, we have some momentum in this direction, we have some momentum straight up. If we kind of imagined an xy plane, we should expect that the net momentum, the total, is going to be somewhere up in that second quadrant. It's got a negative x value and a positive y value. We can't forget our negative sign, and if we do that, we find that the angle is minus 35 degrees. So this actually tells us, because we know it's in this quadrant, this is the angle 35. If this is actually a problem from the back of your book and they want you to give it in the direction, and the prompt for the angle to put in the value is that it's this many degrees west of north, which actually means the answer is this angle. And so, well, we know that the 35 degrees and our answer have to add up to be 90, and so that tells us that our angle would be 55 degrees. Now for the next one, I wanted to do a problem where we were dealing with this, the idea of the graph, because impulse is the force integrated over time. It does give us the change in momentum, but for this particular question, the first thing we're going to do is sort of deal with the fact that this is the area under the curve. And so we want to find, the first question asks, what is the impulse applied to the car from t equals 0 seconds to 4.5 seconds? So we want to go up to here, and basically we want to find this area under the curve. I divided it into actually four parts. This is part 1. Then I did a triangle here, that was 2. Another rectangle, 3, and 4. I could have made it one big rectangle, but I think I just forgot to do that. So we want to find all those areas. Area 1, we're actually told that the height of this right here is 7,500 newtons, so it's 7,500 newtons times 1.5 seconds. Then area 2 is 1/2. The base